Today on AI Paper Podcasts, we are breaking down controlled self-evolution for algorithmic code optimization. It's a new paper from NJU, PKU, and MIDEA ARC, and it really gets at a huge bottleneck in coding agents.
Yes, it does. The paper introduces this framework they call CSE controlled self-evolution. And the whole idea is, look, LLMs are great at generating code that works, functionally correct code.
Right.
But they are notoriously bad at writing code that's efficient. I'm talking about time and space complexity.
And CSE tackles this with what they call 3 pillars. The first is Diversified Planning Initialization. So before it even writes code, it generates totally different algorithmic strategies to avoid getting stuck.
Then there's the second part, genetic evolution. But it's not random. It uses soft selection and this really cool compositional crossover to surgically fix faulty components in the code while keeping what works.
And the third piece is Hierarchical Evolution Memory. It's basically a memory system using a vector DB that remembers what worked and what failed, not just in one task, but across all the tasks it solves.
And the results are pretty clear. CSE consistently beats top models like GPT-5 and Claude 4.5, and even existing methods like AlphaVolve on this big benchmark called EffiBench-X. It's about bridging that gap between it runs and it's production ready.
Okay, so that's the high-level summary. Now let's actually dig in, because if you've ever used an LLM for anything serious, you have felt this pain. You ask it for a solution, it gives you some code, the unit tests all pass.
And then you push it to production and the server just melts.
Exactly. Or, you're on leak code and you hit that dreaded time limit exceeded error. The logic is fine, but it's trying to brute force a problem with a million entries.
That's what the paper calls the efficiency gap. And it makes sense when you think about it. LLMs are just predicting the next most probable word. And the internet, their training data, is just filled with naive implementation.
Tutorial code, basic examples.
Exactly. So the model is statistically biased towards the easiest, slowest solution.
So it's aiming for the most common answer, not the best answer. But, people have tried to fix this before, right? This whole idea of self-correction or self-evolution, where you put the LLM in a loop, write code, test it, fail, fix it, repeat. Why isn't that good enough?
It can work, but it is just incredibly inefficient. The paper argues that these simple generate, verify, refine loops hit 3 major bottlenecks. You just burn through inference tokens for really tiny gains.
Okay, so what's the first bottleneck?
It's called initialization bias. And this one is huge. If your model starts its journey in the wrong neighborhood of the solution space, no amount of small tweaks is going to save it.
Okay, explain that.
So let's say a problem needs a hash map to run in the linear time, right? O of n. But the LLM's first guess is to use a nested loop, a classic O of n squared approach.
Right, and you can optimize that nested loop all day long. You can change the variable names, whatever, but you're never, ever going to get linear time complexity out of that structure. You're polishing a turd.
Precisely. You are stuck in a local optimum. The self-correction loop will just keep iterating on that fundamentally bad idea forever. That's the initialization bias.
Okay, so you're optimizing a bicycle when you really need a jet engine. Got it. What's bottleneck number 2?
Uncontrolled evolution. So when current frameworks try to evolve the code, they often just use random mutations. It's like throwing darts in the dark. They might tell the model, hey, make this faster.
But the model has no idea where the slow part is.
None at all. So it just changes random things. It might reformat the output or swap a while loop for a for loop without actually changing the underlying logic. It's totally undirected. A huge waste of cycles.
And the third one?
Memory amnesia. This is the one that personally drives me crazy with current agents. They are completely stateless. If I spend an hour teaching an agent that, say, recursion depth is limited in Python for one task.
The next day, you give it a new recursion problem, and it makes the exact same mistake.
The exact same mistake. It has 0 long-term memory of these optimization patterns. So CSE is designed specifically to break down these 3 walls.
Okay, let's walk through how they do it. The first pillar is designed to fix that bad starting point problem. Diversified Planning Initialization.
This part is so clever because it intervenes before a single line of code gets generated. Normally, you give the LLM a prompt, and it just starts coding. CSE forces what it calls a strategy sketch phase.
Is that kind of like chain of thought prompting?
It's related, but chain of thought usually narrows down to one path. CSE explicitly asks the model to come up with diverse and distinct algorithmic approaches. It wants a whole menu of options.
So for a string problem, it might come up with what?
It might generate, say, plan A, brute force check of all substrings. Then plan B, use dynamic programming. And plan C, use a sliding window technique.
Okay, so it's forcing the model to consider the entire map of possibilities from the get-go.
Exactly. And then these different sketches are all turned into code for the initial population, what they call P-dollarsers. So from generation 0, you're not putting all your eggs in one basket. You have competition between fundamentally different ideas.
So if that brute force approach inevitably hits a wall, the sliding window candidate is already in the race, ready to go.
Right. It's their solution to the initialization bias.
Okay, let's move to the second pillar, genetic evolution. I mean, genetic algorithms aren't new. You have a population, you select the fittest, you mutate and cross them over. What's different here?
Well, a standard genetic algorithm uses what's called hard selection. You keep the winners, you kill the losers. Simple. CSE uses soft selection.
Why would you ever want to keep the losers?
Because in code, a loser might just have a typo or a small bug. Imagine you have one solution that uses a brilliant, complex algorithm, but it has an off-by-1 error, so it fails most of the tests.
Right, if you just looked at its test score, you'd think it was garbage and throw it out.
And a standard algorithm would. But CSE's soft selection uses probability to keep some of these imperfect candidates around because they might contain the genetic material for the perfect solution.
Okay, don't throw the baby out with the bathwater. That makes sense. But what about the mutation part? How do they avoid just throwing darts in the dark?
That's the controlled mutation. This is maybe the most technical part of the paper. They don't treat the code as just a blob of text. They decompose it into functional blocks, like input-output, the core logic, and boundary handling.
So it's actually parsing the code's structure.
Yes. And then when a piece of code is slow or it fails, the system uses self-reflection to analyze what went wrong. It asks, where is the bottleneck?
So it could figure out, hey, the core algorithm's fine, but the way I'm reading the input is what's taking forever.
Precisely. And this is the control part. It freezes the modules that are working well. It locks the core logic and says, only mutate the I/O block.
That's huge. I can't tell you how many times I've told an LLM to just fix the error handling, and it decides to rewrite the entire algorithm from scratch and introduces 5 new bugs.
It's that catastrophic forgetting problem. Controlled mutation prevents that. It's surgical. You're only editing the broken part, which makes the search way more efficient.
And what about compositional crossover? You can't just splice 2 Python scripts together?
No, you get a syntax error on line 1. This is a semantic crossover. The system actually prompts the LLM to synthesize the strengths of 2 parents. It'll say, take the time complexity logic from parent A, which was super fast, but wrap it in the robustness checks from parent B because parent A kept crashing on edge cases.
That sounds like a senior engineer doing a code review. You know, I like your algorithm, Alice, but you need to use Bob's input validation.
It's the perfect analogy. It's an intelligent synthesis, not just pasting text together.
Okay, so we have diverse starting plans and surgical evolution. That leaves the third pillar, hierarchical evolution memory. How does this solve the amnesia problem?
The authors knew that getting better is about building wisdom over time. So the memory has 2 levels. First, there's the local memory, which just tracks the history for the current task.
Like a change log for the run.
A bit smarter than that. It tracks the change of performance, the delta. If a mutation makes the code 20% faster, it logs a success insight like replacing list comprehension with a generator-saved memory. And of course, it also records failure lessons.
Don't do X again, it caused a timeout.
Exactly. But the real game changer is the global memory.
The memory that persists between different problems.
Yes. This is a vector database that stores all these insights permanently. So when the agent gets a brand new problem, say something about graph traversal, it doesn't start from scratch.
It queries the database first.
It queries the global memory. Have I solved a graph problem before? What worked? What pitfalls did I run into? And it retrieves those past experiences and injects them into the prompt before it even generates the first plan.
That's incredibly powerful. It means the model actually learns and gets smarter over time. It's building a personal playbook of optimization tricks and never has to relearn them.
It turns the system from a static tool into a learning agent. And in their ablation studies, where they turned off different parts to see what would happen, removing the memory component had the single biggest negative impact on performance.
Really? More than the planning or the fancy evolution?
Yep. It turns out that just knowing what not to do is one of the most efficient ways to solve a problem. Without memory, the agent wastes so much time rediscovering mistakes it literally just made last week.
So let's talk proof. They tested this on something called EffiBench-X.
Right. It's a big benchmark, about 623 problems from places like LeetCode and AtCoder. But the really important thing is the metric they use, memory integral.
Sounds like something from my calculus class.
It pretty much is. It's the area under the memory overtime curve. See, you can usually make code faster by using more memory, right? Caching everything. Or you can save memory by recomputing things, which takes more time.
And both of those can be bad.
Right. Memory integral penalizes both extremes. It pushes the model to find the optimal balance between speed and memory usage, which is what real-world engineering is all about. It's basically a metric for your cloud compute bill.
So how did CSE do?
It crushed the baselines. I mean, it obviously beat direct generation from the models, but it also significantly outperformed other sophisticated agent frameworks like SE Agent and AlphaVolve. And what's really interesting is that it was backbone agnostic.
Meaning it worked with any LLM you plugged into it?
Exactly. They tried DeepSeek, Qwen, Claude, GPT-5, and in every case, wrapping the model in the CSE framework made it way better at optimization. It really proves that the agent's architecture matters just as much as the raw power of the underlying model.
Okay, I want to make this concrete. The paper has a case study, a problem called Ringo's favorite numbers. Can you walk us through how CSE actually solved it?
Sure, yeah. This example shows all the pillars working together. So in iteration 1, thanks to diversified planning, one of the first strategies it tried was pre-computation.
Just calculate all the possible answers ahead of time and store them in an array. Super fast lookup.
Super fast, but it needed a massive array. It immediately blew past the memory limit, a total failure. But because of that initial diversity, it didn't just get stuck trying to fix the array. By iteration 5, it had pivoted to a completely different strategy from its initial plans. Square root factorization.
Ah, the classic, the square root of n approach.
Exactly. That move solved the initialization bias. It jumps to a much better algorithmic neighborhood. But the code was still kind of rough. It was timing out on some edge cases.
So now the evolution phase kicks in.
From about iteration 22 to 25, it used that surgical controlled mutation. It identified that the part of the code checking for primes was inefficient, and it rewrote just that specific loop. Then, using compositional crossover, it borrowed an empty input guard from another candidate to stop it from crashing.
Polishing the diamond.
Right. And the paper notes something really cool. The final optimized code looked completely different from the human reference solution. It was a novel logic structure, but it was highly efficient. It slashed the memory integral score.
That's the real aha moment for me. The AI isn't just mimicking code from GitHub anymore. It's discovering new, optimized ways to solve problems on its own.
And that's the big takeaway. We are moving from what I'd call black box generation to agentic engineering.
With a difference.
Black box is you ask GPT-4 for code, you copy-paste it, and you hope for the best. Agentic engineering is where the model operates in a loop. It plans, it prototypes, it debugs, it optimizes, and crucially, it remembers.
It feels like we're finally starting to treat code generation like a real engineering process, not just a text generation task.
Correct. But there is a catch.
Always a catch. Let me guess. Is it cost?
Inference cost and time, yeah.
Right.
CSE has to generate populations of code, run tests, iterate maybe 30 times. It's not happening in real time. You can't use this for the autocomplete in your IDE yet. It takes minutes.
So it's for your really high-value code, your core library, a trading algorithm, something that really needs to be optimized.
For now, yes. But the authors end on this really provocative idea. They suggest that this whole process, this inference time evolution, is just step one. The end game is distillation.
Meaning you train the model on its own successes.
Exactly. Once you have thousands of these evolutionary trajectories, the full history of how the model went from terrible code to great code, you can use that data to fine-tune the base model with reinforcement learning.
So eventually the model wouldn't even need the 30 iterations. It would just know the optimized path instantly because it's internalized all that wisdom from its past attempts.
That's the holy grail, a self-improving model that doesn't just memorize solutions, but internalizes the process of optimization itself. It would see a problem and just instinctively know to avoid the brute force trap.
It's really fascinating. We're moving to a world where AI doesn't just write our code, it architects it.
And hopefully it comments it too.
Let's not get ahead of ourselves. That's all the time we have. A really deep look at controlled self-evolution. If you're building coding agents, it seems like you should stop treating them as stateless text generators and maybe give them a memory.
Absolutely.
Thanks for tuning in to AI Paper Podcasts. We'll see you on the next abstract.